In the last video, we talked about using LEDs and how they're designed. So today we're going to be talking about lasers and how they work. So the key to understanding lasers is to understand stimulated emission. Let me write that down. The key to understanding lasers is stimulated emission. So normally, when we have an electron, which is in the conduction band, and a hole in the valence band, we usually expect what we call spontaneous emission to occur. This is what happens in LEDs. This is when an electron spontaneously and randomly recombines with a hole, and we prominently see this in PN junctions. The problem with this is that every time a photon's released, it's slightly different. They're not the same wavelength. They vary in frequency, resulting in an emission spectrum that's like not very intense. It's usually smoother. So lasers work by stimulated emission. This is when you have an electron in the conduction band and a hole in the valence band, and a photon comes that stimulates this electron to fall down. And because it was stimulated by that photon, it produces a photon that's exactly the same, resulting in an emission spectrum that's much more intense because all the photons are much similar. Now, and importantly, the way at all that you're able to have those electrons there is in the conduction band is using absorption, right? So you send an electron you send a photon and the electron gets absorbed by the photon, causing it to move to the top part. Now, to further understand laser design, one of the key ideas we need to do is make sure that we maximize the amount of stimulated emission. And so that's where what's called like the Einstein coefficients came from. And I will write out these equations. So stimulated emission divided by spontaneous emission. This is something that we want to make as big as possible, right? We want to minimize spontaneous emission, maximize stimulated emission. Now, how do we do that? Is we look at the equations that have been derived to express this, and I'll write them out and then explain what they mean. So this is our first equation. Each of these terms basically describes what's written. And so then stimulated emission. The other thing we want to maximize is stimulated emission over absorption. And this is equal to B21 times N2 over B12 times N1. Dope. So now with this, we can understand, and then let me clarify the variables as well. So N2 is just the number of electrons available in the second state, the excited state, and N1 is the number of holes available in the ground state. And then rho of V12 is the photon density, so the density of photons available that are within the energy state of 1 and 2. So the way we maximize stimulated emission according to this first equation is really just to maximize the photon density. And the way this is done is using resonant cavities, where when you, for example, are able to stimulate a second photon, then resonant cavities allow those newly stimulated photons to bounce back, and this creates a huge number of photons really quickly, because you can see how it would naturally become exponential in growth, the number of photons. And that is another way to increase stimulated emission, because you just have more photons going around being able to stimulate. So cavities are a really key invention to lasers. And then the other way is to basically maximize the number of electrons in the N2 state compared to in the N1 state. And the way to do that is something that people have designed, or scientists have designed, called population inversion. Population inversion. So what is population inversion? Basically, the idea is that suppose you have an electron that gets excited and goes to the second state due to absorption, due to absorption. Then usually what ends up happening is just due to spontaneous emission, it falls down, which is not really very good for us. So population inversion is a way of designing your laser so that it absorbs enough energy that the electron will go to state 3. And then if spontaneous emission occurs, it's only falling to state 2, where it can still be hit by an electron, by a photon, and stimulate emission. And so this is essentially the way that stimulated emission works. Population inversion works by creating this third state that the electrons can be in. Now, how we can now design this laser using like the semiconductor principles that we understand is using a PN junction, because a PN junction readily has available the key property that it which is its depletion depletion region, where holes and electrons are actively recombining, which is what we need to stimulate emission. So we can draw our band diagram. So a couple electrons here, and probably a lot more electrons here, and then a couple of holes down here. Excuse me. So I drew this, and so in the depletion region, it's common to see how that's a place where holes and electrons recombine, and so the way that we can induce population inversion here to maximize stimulated emission is by injecting a bunch of carriers into it, which makes a lot of sense, right? So you forward bias it, which injects a bunch of holes into the p-type and a bunch of electrons into the n-type. And so you can imagine that suddenly the depletion region is like filled with layers of electrons and layers of holes, which is what you need to create population inversion. And so this population inversion stimulates stimulated emission. Now the other thing to mention about this the last thing to mention is another common design for lasers, which is, so what we've been looking at is an edge-emitting laser, because if we look at our PN junction design, there's this very thin area we have, which acts as a waveguide, collecting all of the all the photons before releasing it. This is called edge emission. The other way we can do it is surface emission, which is where you have, and I'll discuss right now what's called a surface emitting laser, which is where you have a large surface and then you propagate photons through here that stimulate emission using something called quantum wells, which we'll not go into, but the main point being made is that rather than having this like waveguide feature, it just sends electrons from the surface, photons from the surface. And there's advantages and disadvantages to both of these. This is usually more low power, which means it's lower cost and works at shorter distances, whereas this option right here of edge emission is higher power and usually more expensive but can travel larger distances. And so those are the key concepts regarding lasers. I hope you liked the video. If you have any questions, please feel free to comment. I will answer them, and then have a good day.